just seen, what we've just seen is the fundamental theorem of calculus. Part 1. Part 1. There's a part 2. The Fundamental Theorem of Calculus, Part 1. It says the following. Let me just state it completely. If f of x is continuous on the interval from a to b, then the function a of x, which is given by the integral from a to x of f of t dt, where x ranges from a to b, so this function a of x this function is continuous on the closed interval from a to b and differentiable on the open interval from a to b. And even more, we know what its derivative is. A prime of x, which is the derivative of the integral from a to x of f of t dt, equals f of x. So this says, when we have a function, f, and we look at this area function, which is this integral function. This function is taking an integral, this definite integral. And when we take the derivative of that function, we get back what we started. This is crazy. That these two concepts of derivatives and integrals are related like this. Derivatives are about rates of change. Integrals are about sums. Why in the world would rates of change and sums have anything to do with each other? But the Fundamental Theorem of Calculus shows that they are very, very closely related. Because when we have a function and we integrate it, and then we take the derivative of that integral, we get back the original function. This is such a powerful result. So this is part 1 of the Fundamental Theorem of Calculus. And so I told you that we were going to be able to calculate definite integrals, right? And I said, we're going to need a way to actually calculate definite integrals. This doesn't help us do that yet. But what this does help us do is get part 2 of the Fundamental Theorem of Calculus, which is, computationally speaking, perhaps the most important result in all of calculus. And it will help us calculate all of these definite integrals that we wanted to calculate, that we've had to use all these Riemann sums in order to calculate. We won't need to do that anymore. So let me state what part 2 of the Fundamental Theorem of Calculus is. can I spell fundamental? Fundamental Theorem of Calculus, Part 2.
This is different from the second fundamental theorem. Right? There's not a second one.
No, there's just the Fundamental Theorem of Calculus. There's Part 1 and Part 2. Okay, so this is what this Fundamental Theorem of Calculus Part 2 says. So if f is continuous on the interval from a to b, and capital F is an antiderivative of little f. So in other words, capital F prime equals little f. Then the definite integral from a to b of little f dx equals capital F of b minus capital F of a. So if we have an antiderivative of little f, we want to evaluate the definite integral of little f from a to b. All we need to do is plug in the antiderivative at the endpoints and subtract. Let's see why this is true. Let's see why this is true. Okay. So why is Fundamental Theorem of Calculus Part 2 true? Well, we know that a of x is an antiderivative of this function. Right? That's what this says. Saying that a prime equals little f. That says that capital A is an antiderivative. So we know that a of x, which is the integral from a to x of f of t dt, is an antiderivative of little f. That's what the Fundamental Theorem of Calculus Part 1 says. Fundamental Theorem of Calculus Part 1 says that if we have some function little f, the area function is an antiderivative of little f. That's what the Fundamental Theorem of Calculus Part 1 says. So we know that this function a is an antiderivative of little f. So now suppose we have some antiderivative big F. So given an antiderivative big F, we know that big F and A have to differ by a constant. We saw that two antiderivatives of a function have to differ by at most a constant. We saw that was due to the mean value theorem. Right? So the mean value theorem shows that F, let me write it as A of X, F of X equals A of X plus some constant C. So now, let's evaluate f of b minus f of a. Well, that is, using this, that's a of b plus c minus a of a plus c. And now, let's use the definition of a. So this is the integral from a to b of f of t dt plus c. I can cancel out the c's, right? Plus c. When I subtract, the c's cancel out, right? Minus the integral from a to a of f of t dt. But what's the integral from a to a of f? It's 0. That's 0. So I get that the integral from a to b of f of t dt equals f of b minus f of a. So that's the fundamental theorem of calculus part 2. That the integral of a to b of f of x dx equals f of b minus f of a. Remember we said that the variable of integration doesn't matter, it's a dummy variable. So this, when I have a t here and an x there, it's the same thing. So that's the fundamental theorem of calculus part 2. This result also should blow your mind. Because this thing on the left here, the way we define this is defined as a limit of Riemann sums. How are Riemann sums defined? They're defined by taking these rectangles, taking function values at all of these points, and then taking the limit as n goes to infinity. We need to know the value of f at like every single point in the interval a to b in order to evaluate this definite integral using the definition. Right? You need to know so many x values in order to evaluate this. And you need to know the function value of all these different x values in order to evaluate this. What the fundamental theorem of calculus part 2 says is no, you don't need to know that. You only need to know the function at 2 values. At a and at b. It's crazy. It's insane. And it's so powerful that, so all of that work we did to calculate these definite integrals using Riemann sums, using areas under curves, all of that stuff, it's good. It's important that you know it because it's probably going to show up on tests. But from a practical standpoint, it's completely useless because of this result. This result is so powerful. Both of these results, part 1 and part 2, together, they form the core of all of calculus. They connect differential calculus and integral calculus. They connect these two seemingly disparate branches of math. Integration, differentiation, they don't seem to have anything to do with each other. And this result brings them together. It's such an important result. It's the most important thing that you will see in this class. If you take Calc 2, you won't see anything as important as this. This is the most important thing that you will see in your calculus education, the fundamental theorem of calculus. It is so incredibly important. Are there any questions? Okay, let's use these to do some examples. So there are two types of examples. We can do part 1 examples, and then we can do part 2 examples. So part 1 examples are you're given a function, and then you're asked to take its derivative, and the function is in terms of some integral, and then you just have to use the fact that the derivative of the integral is the thing inside the integral. So that's what part 1 examples are like. Part 2 examples are you have to take the integral and you use the fact that you can't find an antiderivative and you just take the antiderivative at the endpoints. So let's do some part 1 examples, then we'll do some part 2 examples. Okay?